Okay, so in this lecture, we're going to look at magnetic vector potential, the magnetic vector potential. So just to kind of summarize what we have already seen in electrostatics, we have Coulomb's law and the equivalent to that in magnetostatics, the Biot-Savart law. We had Gauss's law for electrostatics and the equivalent to that for magnetostatics would be Ampere's law. We know that the curl of an electric field for electrostatics is 0. There's no curl, there's no swirl in the electric field. And the divergence of a magnetic field is 0. In electrostatics, we explored the concept of electric potential, which was defined by the line integral. The change in electric potential was minus the line integral of our electric field, or the electric field was equal to minus the gradient of the electric potential. So in magnetostatics, the equivalent to the electric potential is our magnetic potential. And so we're going to find this magnetic potential. So if you remember when we were looking at the electric potential, we started off with the theorem of curlless vector fields, which stated that if the curl of a vector field vanishes everywhere, then the vector field can be written as the gradient of a scalar potential. So V was our electric potential, because our electric field is curlless. There's another theorem this time for divergence-less vector fields. If the divergence of a vector field vanishes everywhere, then the vector field can be written as the curl of a vector field. So we know that our B field is a divergence-less vector field, so it can be written as the curl of a vector field that I'll call A, and that is our magnetic potential. So let's find Ampere's law in terms of our magnetic potential now, which is the curl, the B field is equal to the curl of the magnetic potential. I'm going to take the curl of both sides of this equation. Then I'm going to use a vector ID for the right-hand side of the equation. This vector ID here So if I use that vector ID for this right-hand side, this is what I get over here. And then on the left-hand side, the curl of B, I'll apply Ampere's law. The curl of our vector field B is equal to mu naught J, J being the current density, volume current density. So I get mu naught J is equal to the gradient of the divergence of our vector field minus the Laplacian of the vector field, magnetic vector field. So we have this equation relating our magnetic vector potential and our current density. So if you remember for the electric potential, you can add a constant to the potential without changing the electric field. In other words, we could choose the origin of our electric potential. So let's check this for a 1D case where electric field is minus d dx of our electric potential. If we add a constant to the potential, c, we get v prime is equal to v plus c. So E prime would be minus d dx of v prime, so v plus c. And multiply that out. C is a constant, so d dx is 0. So I get E prime is minus d dx v, so E prime is equal to E. So we just proved that we can add a constant to the potential, but the electric field remains the same. For our magnetic vector potential, you can add a function whose curl vanishes to the potential without changing the magnetic field. Okay, so let's add a curlless function to the magnetic vector potential, C. So A prime is equal to A plus C. B prime would then be equal to the curl of A plus C. They should have vector symbols, the A and C, on them. So B prime is equal to the curl of A because C is a curlless function. So we find B prime is equal to B. So we can add a curlless function to our magnetic potential vector without changing the magnetic field. So the gradient of a scalar is always curlless. So we can always add the gradient of a scalar to our magnetic potential without changing the magnetic field. So just like we're free to choose the origin for the electric potential, we're free to choose this gradient of the scalar for our magnetic vector potential. And this choice, like choosing the origin for the electric field, in this case, choosing this gradient of a scalar for our magnetic potential, is called choosing the gauge of our magnetic potential. One gauge that is often used is called the Coulomb gauge. And the Coulomb gauge is a gauge in which the divergence of our magnetic potential A is equal to 0. And if we look at Ampere's law in Coulomb's gauge, this first term goes to 0. So you have the gradient of A is equal to minus mu naught J. And this should be reminiscent of Poisson's equation. If you remember Poisson's equation, it was the Laplacian of our electric potential is equal to minus rho over epsilon naught. And since we know the electric potential is equal to 1 over 4 pi epsilon naught integral 1 over r rho d tau, we can compare these two. So since A is equal to minus mu naught J, V is minus rho over epsilon naught, replace things in here to get an expression for the magnetic vector potential in our Coulomb gauge. So instead of a epsilon naught, we have a mu naught. Instead of a rho, we have a J. So we have the the magnetic potential vector A is mu naught over 4 pi 1 over r j d tau. Okay, then you'll be doing this problem where you're going to find the magnetic vector potential of an infinite straight wire carrying a current I, both outside and inside a wire of radius r. And then we will do this clicker question. And that's it for this set of slides.